Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is ASCE 7 2022 Response Spectrum Analysis in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They're both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout this presentation. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. As far as the content over the next hour today, we do want to begin with the modal analysis add-on within the RFEM 6 program to calculate the structure that we see over here on the right for the natural frequencies, periods, and mode shapes. We'll then move on to the response spectrum analysis add-on to calculate the seismic loads according to the ASCE 7, the latest 2022 standards. We'll talk a little bit more about how we can combine these seismic loads with the other load cases using what we call result combinations. And the final add-on we'll touch on is the building model. So this will allow us to view more information specific to the various story levels in our multi-level story structure for our seismic results. And finally, we'll talk about base shear, drift, and P delta effects and how potentially we can scale up our seismic forces. So with that said, we will immediately begin within our RFEM 6 program today. So when you do create a new file, you are presented here with the base data dialog box where we give it a model name. The type of model will be in a 3D environment. And under the second tab, these are all of the various add-ons that we have available in the program. So for those of you joining us today who are not familiar with our program setup, RFEM 6 is the base program that allows us to fully model our structures where we have access to all the cross sections and materials from all the various standards. We can apply loads and we can run a full static analysis. But when we need a more advanced analysis, like for example today with dynamics, we would need the relevant add-ons. If we wanted to carry out the design according to the various materials listed here, as well as the design standards, then we would need to activate these design add-ons. So more or less, you create a software package that's specific for your particular design needs. So for today, we will begin without any particular add-ons. We want to work initially within the base program alone. We will generate the load combinations here according to the ASCE 7, the latest 2022 standard. Notice we also have the NBC standard available here within our dropdown. So for the sake of time, I have already modeled our structure that we will be working with today, but I do want to go over a quick model review. So this is a reinforced concrete structure. We have the material 4000 PSI assigned to all elements that you can see here. The cross sections, we do have some cross sections running up through the interior for our columns of the structure, just basic rectangular sections. We also have some beams spanning between the shear walls at each level shown here. And finally, we have our 2D surfaces. So the elevated slabs have a thickness assigned to them as 10 inches, as well as that same concrete material, 4000 PSI. The wall elements are going to be a thickness of 11 inches. And finally, we have our slab on grade element down here at the base of the structure. This is going to be quite a bit thicker at 32 inches thick. Now, we also have our support conditions. So I went ahead and applied a surface support to our slab on grade here. And this is just going to represent the soil stiffness. You can see here, this is applied only in the Z direction with a spring constant here set pretty high. All the rest of the degrees of freedom are released for this simple example. So this would be the information that we would get directly from the geotech engineer. Now, in the lateral directions, I did apply a line support here only at the boundary lines of the slab element itself. So if we take a look at these particular line supports, you can see that I have restrained them in the lateral X and Y directions. All other degrees of freedom are set to release. So this all just depends on your project, and of course the support conditions can vary. So now that we have reviewed the model, let us take a look at the loading. Within our drop-down box up here at the top, I have a few load cases already defined where we can take a look at the loads also applied to the structure. So for our dead load, we have a simple surface load applied at each level. Same concept here for live load, just with a modified magnitude at the lower levels here. We also have a roof live load, again, accounting for the openings here. And finally, we have a snow load. So with all of these load cases, we are going to also take a look at them within our load cases and combinations dialog box. And we'll actually be within this dialog box quite a bit today. One thing that I wanted to point out with the load cases, I do have an additional structure modification applied here to each load case. This is specific to the ASCE standard for members and surfaces, where we can apply that I crack factor for reinforced concrete to reduce the stiffness for our analysis. Again, required by the code. I'm not going to go into much detail with this today. We do have previous webinars on both the ASCE and the CSA 823.3 that you can refer to. So now that we have our 4 static load cases here, I'm actually going to make a copy of my existing dead load case. And the reason why I want to make a copy of this is I want all of the loads that have already been applied under the dead load case to also be applied here in load case number 5. This is going to have a new load case name here for our vertical seismic. And I'm not quite yet ready to jump into the response spectrum analysis, but I am going to apply the seismic loads as a static load type to begin with. So therefore, we can rename this one to vertical seismic. And I also want to specify here directly from the code section 12422, and in particular equation 12.4-4a, exactly the equation that I will be applying for this load type. So referencing this equation from the code, this will be a factor of 0.2 multiplied by SDS, multiplied further by our dead load. Now, again, the advantage here is that we are just going to apply a static analysis. I do want to modify here the action category to earthquake load vertical. This just tells the program how exactly we want to combine the load case with the other load cases here based on the ASCE 7. But the self-weight was automatically copied over here as well. So this is part of our dead load to consider within this equation, but taking into consideration the 0.2 factor, and for my example today, the SDS is going to equal a value of 0.72. I multiply those by the negative 0.1 factor for, the negative 1 factor for self-weight. This gives us a value of 0.144. Now, if you remember too that under my dead load case, we also had an applied additional dead load at each of the story levels that we want to consider for the vertical seismic. So therefore, I'm going to select all of the elements within the graphical view here, and we want to double click on this surface load itself to make a modification here to the load magnitude. So again, referencing the ASCE equation, we will take into consideration the 0.2 times 0.72 multiplied by this initial dead load, 0.02, and we're going to get a value here of negative 0.003. So a very small load to consider in the vertical direction. So that vertical seismic load is complete. So you can certainly use the base program alone RFEM 6 to apply any seismic loads as a static load type if you prefer. But now we want to move into the horizontal or orthogonal seismic loads. And this is where we want to activate now those particular add-ons. So what we're going to do is to visit the base data dialog box, which we can access here directly within our quick tools. And under the add-ons, as we revisited first at the beginning of this webinar, we can go ahead and activate here the modal analysis and the response spectrum analysis. So when I click OK, I am going to go back into my load cases and combinations dialog box. And we'll begin first with a new load case here that we will give it the load case name of modal. The analysis type is going to be set to modal analysis. This is available to me because I have activated that specific add-on under my base data. And then we'll just simply move through the various settings here. So I'll take a look at the modal analysis settings directly within this dialog box, where the method for determining the number of modes by default is set to user defined. So this is what we'll be utilizing today. But alternatively, I can set the effective modal mass factor to something like 90%, which is required by the code, in order for the program to determine how many eigenmodes are required. This option is also available here for natural frequency. So again, moving forward today, we will select 10 modes to solve for our initial modal analysis. Now, as far as the method for solving the eigenvalue problem, we have selected here the Lenkos solver, which is available by default. This allows a pretty quick convergence and also calculates the lowest number of eigenvalues. Now, alternatively, if we use one of these alternative options here within the dropdown, you will see that the root of the characteristic polynomial is the only solver available. Alternatively, with user defined, we also have the subspace iteration. So I'm not going to go into any detail specifically on these solvers, but you can always click on this info help button down here in the lower left. That will take you directly to the online manual for RFEM 6 to explain the solver types in more detail. The type of mass matrix by default is set to consistent. This is what we will move forward with today, but there is also the diagonal and unit mass matrix. Again, that help manual will go ahead and explain those options further. I am only interested in carrying out the seismic loads in the orthogonal horizontal directions, X and Y. So therefore, I've already applied the vertical seismic loads in that additional static load case number 5. So I'll go ahead and deactivate my masses then in the vertical direction. I'm also not interested in the masses, the torsional masses about the global X and Y axes, but I might be interested in the torsional modes about the vertical Z axis. So I can go ahead and leave this active here. Now, under the settings, the mass conversion type, we can convert all Z components of the loads, whether that's up or down, to masses. The second option is only to convert the downward loads to masses. And the third option, probably not used so often, is to take all forces, whether it's in X, Y, or Z, and convert them to masses. In our case today, we only have downward loads that we will be considering, so this first option is sufficient. Over on the right, we have the ability to neglect masses. I'm not going to neglect any masses right now, but we will revisit this in just a minute. So now that we have those settings applied here, we have the ability to import the masses from a load case or load combination. And you'll see here only my relevant load cases are shown. But when we refer to the code section 1272, we are given the effective seismic weight here that combines several of these load cases together into a mass combination. Now, we certainly could create this mass combination manually, but we want to take advantage of what the program can automatically create for us instead. So for this, I'm going to jump to the design situation. The design situation is normally used to generate our load combinations. You can see here that 2 design situations were created for our factor load combinations and our unfactored load combinations. And we will get into this topic later on in regard to the load combinations themselves. But right now, I am going to create a third design situation. And within my drop-down box, I'm going to scroll all the way to the bottom here where I have the option for effective seismic weight. And this is going to reference the ASCE 7 directly to create that mass combination for us, considering dead, live, roof live, and also snow. So now when I jump to the load combinations, we can see the mass combination generated automatically for us. The problem here, though, is that I don't see that roof live load considered. And the reason for this is that the roof live load could be optional within the code, just depending on our or project or specific settings. So therefore, under the load cases, if you do visit the roof life here, under the additional settings, we have this checkbox to consider that within the effective seismic weight mass combination. And now the program will regenerate that mass combination for us. And sure enough, we see all of the relevant load cases here with the applied factors that will be used for our mass conversion. So going back to the modal analysis then, we can now use our drop-down box to select that mass combination directly. Okay, so now that we have created here all of the input settings for the modal analysis directly, we can go ahead and just run this calculation quickly. So you'll notice the first thing that the program does is to generate the mesh for all of our elements here in the background. Considering all of the openings, the mesh looks quite nice. Then we are going to calculate through those 10 different eigenmodes that I had essentially set within those settings so that the program will go ahead and take a look at the natural frequencies here for each one of those. We are converting, again, the masses from that mass combination to take into consideration with the modal analysis. So once this calculation is complete, we are presented here with the results. So we might make some modifications here graphically just to better see our results. For example, we can turn off the FE mesh up here at the top within our quick tools. Also, the members are represented by one-dimensional lines. If we want to make a change to that, over here within the navigator, we can select here the members under the deformations to change these to cross sections rather than single line elements. So currently we're viewing the mode shape here, and within this dropdown, we can take a look at the 10 different mode shapes that we have solved for, and we'll see the structure response adjust accordingly. The scaling of the mode shape is also set here down at the very bottom of our navigator. You can see by default, we are going to scale them to a factor of 1.0, considering the translational directions, but you could make modifications to this if you see fit. Again, we probably won't. We'll typically leave this as the default scaling set here. So in addition to the mode shape, we can also activate the display of our masses. And if I zoom in here and maybe turn this into wireframe view, we can also decrease the size of the masses here. This is showing us at every single FE mesh point exactly the masses that we are considering for this modal analysis from that mass combination. So in addition to our graphical results here for the mode shape and displaying of the masses, we also have our table results. So we use our drop down here to set this to the modal analysis, where those 10 different mode shapes, again, are shown here, along with the relevant angular frequency, natural frequency, and of course, the natural period. The second tab is going to be very important for us because this is going to tell us our total mass participation here for those 10 different mode shapes. So when I look at the mass participation and this last row given here in the X direction, it's 57%. In the Y direction, it is 55%. And when we refer to the code section 12911, this tells us that we need to meet a minimum of 90% mass participation. So we're quite a bit away from this value. So there are a couple different approaches we can take in order to modify this to try and reach that 90%. The first is to simply solve for more eigenvalues. The problem, though, is that we have a pretty thick slab here with not only self-weight, but also the additional applied loads to this structure, and that mass is feeding directly into these supports. So for this particular structure, it's going to be hard to reach that 90% when we are considering this slab. So this might be a scenario where we want to deactivate the mass from the slab element directly. Now, this could also be useful too if you have a structure with a lot of members and you have a lot of what we call local modes with not much mass participation going on. Perhaps we want to deactivate the mass from those individual elements and instead kind of bunch them together in a single mass. We have what we call the mass loads available as well. So up here within our tools, we have the ability to always apply something like a new nodal load set as a force. But in this dropdown, we can always apply a mass load as well. And this would be taken into consideration within this modal analysis. So this is available not only for point loads, but also member, line, or surface loads. Now, again, for our example today, what we're going to do here is to jump back to the modal analysis, and we'll go back to the settings here where instead of neglecting no objects, we want to change this to user defined. And I'm going to select here a surface element, and I'm going to graphically select this slab. This is surface number 1. I could directly type it in here as well. We will neglect the masses in all directions. I click OK. The program tells me it needs to delete the results. And essentially I want to run through this calculation again. So this is really identical to what we just calculated previously. The program doesn't need to regenerate the FE mesh. We did not make any modifications to the geometry of the structure itself, but rather the only thing that we did was neglect the mass in that slab element. So self-weight, dead, live, any of the other applicable loads that were converted to mass. We are still solving for a total of 10 different modes. So once this is done with the calculation, we immediately jump to the table and we see here in the X direction, we have 94% mass participation, and in the Y direction, we have 91% mass participation. So that looks quite good. That's exactly what we want to meet at a minimum. So this is sufficient here for our modal analysis. What else you could verify too is if we activate the display of the masses, you'll notice we have no masses now on our slab element. All right, so now that the modal analysis is complete, we have the required mass participation of 90% in the orthogonal directions. We want to move forward now with our response spectrum analysis. So before we create this new load case for the response spectrum analysis, I'm going back to this base tab here where we're generating our load combinations according to the ASCE 7, but we can activate here the parameters. So for the first part of this example, I want to emphasize that we want to consider the same redundancy factor in both directions, X and Y. Now, alternatively, if we weren't working with redundancy, but rather overstrength factors, this would also be applicable, the same workflow. That essentially this first line is where we set what that redundancy factor is. The additional lines here in the X and Y are completely irrelevant. They can be ignored for this first part of the example. So again, assuming we have the same redundancy factor of 1.0 in both directions, or with overstrength, same factor in both directions. So under the load cases, I'm going to create yet again a new load case here, and we're going to give it the name RSA for response spectrum analysis, but I want to emphasize again that we are going to put both the X and the Y response spectrum analysis in this single load case because again, the redundancy factor is the same in both directions. In my drop-down box here, I choose response spectrum analysis because I have that add-on activated, and we can see the settings adjust automatically. The spectral analysis settings, let's take a look at this. This would essentially be where we set the modal combination method according to this drop-down, as well as the combination of directional components. So for this topic, I'm going to go back to the PowerPoint because I do think it's really important to understand these settings that we are applying here to our response spectrum analysis. So starting first with the upper dropdown, the modal combination method. Well, when we finally do run our response spectrum analysis, what we're going to see here is our 10 different mode shapes. And when we apply the response spectrum analysis, we then get 10 different results here in the X and 10 different in the Y. So we need to somehow combine these so that we get a single result in the X and a single result in the Y. And we do so within this drop-down box here with setting either the square root sum of the squares. The equation is shown here, pretty self-explanatory. We also have the complete quadratic combination, the CQC. You can see the modified equation here. A big difference is this correlation coefficient epsilon, where we can consider damping. The third option is the absolute sum. Again, probably not utilized too often. Most likely for following the code, we will set this to the SRSS or the CQC. So once we have applied one of these rules, we will then see a single result in the X and a single result in the Y for our response spectrum analysis. Now, a problem though with the SRSS or the CQC combinations is that the corresponding internal forces are lost. We see this because we take the square and then the square root. So in our results of the single X and Y direction, we may have over-designed here our structure because we're going to consider the max internal forces. So for example, a member, we will consider the max moment along with the max axial force, max shear force, and we know in reality these max forces are not all going to occur at the same time. So what we do to alleviate this is to activate this equivalent linear combination. This is going to give us more realistic results and the correct signage. So what we will essentially have considered with an internal force for a member, for example, is the max moment, but then the corresponding axial force rather than the maximum axial force also being considered concurrently. So with this checkbox, you can see here the modified equations for the SRSS or the CQC rule. Moving on now to that second dropdown within the same dialog box. This is the combination of the directional components setting. And I want to emphasize here that this is only applicable when we have both the X and the Y response spectrum analysis in a single load case. And this will make more sense as we move through our example today. But again, we do have the scenario of X and Y in a single load case. We saw from the previous slide, we now have combined to get a single result in the X and a single result in the Y. Well, we know in reality, earthquakes don't necessarily happen in just the X or just the Y. So how do we further combine these together? And this is what this second dropdown is going to give us. We have the option to once again combine using the SRSS rule given here. But most likely we're going to choose the scaled sum. And for this is the 130 rule. We reference the code, in particular section 12512, where we will take 100% of the X forces combined with 30% of the Y and vice versa, 100% in the Y, 30% in the X. The third option, absolute sum, we would take 100% of the X and add it to 100% of the Y. Again, probably not used so often. Most likely we are choosing the scaled sum. So what we'll see in our results then is the program automatically combine these together, just like what I mentioned with the 130 rule, 100 in X, 30 in Y, and vice versa, 30 in X and 100 in Y. Okay, so going back to RFEM then, we want to choose our first dropdown here for the periodic response combination to SRSS. Notice that when we do select CQC, damping is available to us. We will want to turn on the equivalent linear combination. And then as far as combining here, the directional coefficients, we follow the ASCE 7 to set this to the scaled sum for the 130 rule. And now we just continue to move on down this list. We do want to import the modal analysis from load case number 6. We only have one modal analysis load case. This is nice though in RFEM that if you want multiple modal analysis load cases, you can do so. Perhaps if you're playing around with the different masses and you want to test out some different scenarios, you can do so. The action category is automatically set to horizontal earthquake forces from the ASCE. Again, this will help combine these later on into load combinations and result combinations. We also have the ability here to consider accidental torsion. So this comes from the code, section 12842, that if our structure maybe has a non-flexible diaphragm, if we have irregularities, we may want to consider this additional accidental torsion with our seismic loads. And this is 5% of the building length in both directions. You can see the building length is automatically determined by the program. You could also override that if you would like. The save results of all selected modes. I will turn this on. This just refers back to the PowerPoint that I had just explained here, where we have all the different mode shapes in the X and Y direction. We can actually view the results for all of those mode shapes within the program as well. This last option, this is completely irrelevant when we are combining X and Y together. So nothing to worry about right now. We'll get back to this later on. The response spectrum. Remember, we are combining X and Y. Therefore, we activate the response spectrum in both the X and the Y directions. Z has already been taken care of in the static load case, so we'll leave that turned off. Now, by default, the program will go ahead and create the response spectrum type according to the ASCE 7 for a 2-period as listed here. So I'm going to go back to the PowerPoint to discuss this in more detail, the design response spectrum in section 11.4.5. Today, we will be focusing on the multi-period response spectrum from 11.4.5.1. As most of you know who are joining us today, this was a pretty significant change within the 2022 standard, that we now have introduced this multi-period response spectrum that has 22 response periods in comparison to the previous 2-period response spectrum, which is still offered in section 11.4.5.2. So you can see the difference in those response spectrums over here on the right-hand side. This was taken directly from the ASCE 7 website as linked here at the bottom. This is just a helpful article that explains this multi-period a little bit further. So certainly looks a bit different here when we take a look at the response spectrum itself. Now, this was introduced for improved accuracy, especially for soft soils or structures with long periods. Now, this particular article also states that essentially when we are running a modal response spectrum analysis from section 12.9.1, which is what we're doing today, we are required to run this multi-period response spectrum. We get this information directly from the ASCE hazard tool. I've linked it here. We'll certainly be utilizing this today to pull that USGS seismic design data to generate this response spectrum. One other interesting point I put here down at the bottom is that, yes, we will certainly use a multi-period for our response spectrum analysis, but later on, we are going to talk about scaling up possibly these seismic forces when we compare the base shear to the equivalent lateral force procedure and that base shear that was calculated from there. This article does tell us that, yes, again, apply the multi-period for the response spectrum, but when you calculate the base shear outside the program according to equivalent lateral force procedure to scale up the base shear itself, that we would use the 2-period. You wouldn't want to use the multi-period for both. This results in a little bit of an over-conservative design. Again, we'll talk about that in just a bit. Okay, so I'm going to go back to RFEM, and we're going to create a new type here set to user defined. And we could even rename this. We'll call this ASCE 7, again, the 2022, but this is going to be the multi-period. And for this information, we are going to visit the ASCE 7 hazard tool. So I've already input my information here for Charleston, South Carolina. We're just using that same example from the ASCE. I have a risk category set here, soil class of stiff soil, and we get our data shown to us directly on this website. We also have the ability here to generate a CSV file. So we open the CSV file in something like Microsoft Excel, and it's quite simple. We have our 22 periods shown here with the relevant accelerations. So I'm going to take these period values and I just simply hit Control-C. I go back to RFEM here and I click in this first cell and I hit Control-V. Now everything is red right now, and that's just simply because we need to go back to the Excel file and do the exact same thing here with our accelerations. So we'll go ahead and highlight all of them, Control-C, we go back to RFEM here, and I click in this first cell and Control-V. And now we see this exact same data populated here within RFEM. So I can click OK, and then I want to ensure that I select this multi-period here from my dropdown rather than the 2-period. We also have this scale factor. And this scale factor is going to come into play several more times in the rest of this presentation. But to begin, I want to discuss the modal response parameters in the code section 12912. So if we are applying this response spectrum analysis for force-related design, so this is for story drifts, support forces, or for member forces, the code tells us that we need to take this response spectra, in our case, it's this multi-period, and divide it by the response modification coefficient, further divided by the importance factor. If we're using this response spectrum analysis for a displacement related design, so this is for displacements or the structure's overall drift, we need to once again take that response spectrum, our multi-period, and multiply it by the deflection amplification factor divided by the importance factor. So we might be wondering, well, how do we take into consideration these factors? Well, we do so directly with this scale factor input. So for example, if we are doing the force-related design, we would multiply here I sub E over R, or we could take the displacement-related and multiply C sub D over I sub E. Okay, so we'll go back here to RFEM to carry out then the rest of our input for this response spectrum. Again, that scale factor is shown here. We'll leave this just as 1.0 for our example today. The final tab, though, is the selection of modes. So we have our 10 different mode shapes here from that modal analysis. And one efficient setting might be to go ahead and activate here the ability to not consider the modes that aren't really contributing a whole lot to the mass participation. You can see the default value set here is 0.05. You can make modifications to that. The reason why is if you have 100 modes that you've solved for, there may be many that really aren't contributing too much. This is going to speed up the calculation. This is going to decrease the amount of result output, but we always want to make sure here that we're still meeting the mass participation. So for my example today, we could deactivate modes number 7 and 8. You can see we're still meeting that 90% mass participation in both directions. So that looks quite good there. Okay, so now that we have input in all of this information, we're ready to run our calculation. Now, this will take just a minute to solve, so I'll go ahead and toggle here to a model where we have already run this calculation where we can directly look at our results in RFEM. So once that calculation is complete, I'm looking at that same load case for the response spectrum analysis. And you can see here within my dropdown exactly what I explained in the PowerPoint. We have all of our different mode shapes here in the X and Y direction. We're combining according to the SRSS rule to get a single result in the X and a single result in the Y. And then we further can take a look at the 130% rule here that are applied to both the X and the Y direction. Now, one thing that the default option here up at the top is this scaled sums envelope. So we don't have to worry about, okay, what's the worst case scenario with 100% in the X versus 100% in the Y? The program does this automatically for us and gives us an envelope solution considering all the options within this list here. So with this scaled sum envelope, we're currently looking at the global deformation. We've already applied the seismic loads to our structure. We've run the analysis. So now we're looking at the actual results here from the horizontal seismic loads only. Now, because this is an envelope solution, we have this option here to view both the max and min values graphically together, or we could view just the max values or just the min values. Now, in addition to the global deformation of these seismic loads, we're probably also interested in the internal forces here for something like our member elements. So we can activate here the axial forces, we can view the shear forces, or maybe bending moments of both the beams and the columns. In addition, we're probably also interested in the internal forces for our surface. So I could take one of the elevated slabs here and I'll create a user-defined visibility. And we can activate the bending moments of this first level slab in the X direction, or take a look at bending moments in the Y direction, and so on. In addition to the members and the surfaces, we also have our support reaction. So I'll cancel out of this visibility, and what we should see are the support reactions here for the line supports only. I have no vertical load, so I'm not going to see any response or any support reactions in the vertical direction, rather only the horizontal directions from the line supports themselves. In addition to viewing everything graphically, we can jump to the spectral analysis here in the table results, and we can view the internal forces of the members or the surfaces or the results by the line, for example. So here are those same support forces that I'm viewing graphically. Kind of see the red arrow there, syncing with my table output. We can export this to Microsoft Excel with the click of a button directly here within the table if we like. So again, for further sorting capabilities, everything is available to us graphically here, but also within this table format. So now that we have carried out the results here for our seismic loads, we're likely wondering, okay, well, how do we combine now with the other load cases? So when I jump to the design situations, you'll see here again that the program creates these two design situations, factored load combinations from the ASCE E7 and unfactored load combinations. So these are more or less just grouping together all of our load combinations together. We can view these load combinations here under the last tab. And when I take a look at my factored load combinations belonging to that first design situation, I really don't see any of the earthquake forces listed here. And the reason why is because we need to go back to the design situations and actually create here a new definition type. And that's because we've separated out the seismic load combinations here in additional design situation options within this dropdown. So we see numbers 6 and 7, which just reference the ASCE E7 directly for the redundancy factor. But we also have 6 and 7 here, including overstrength, if we were taking that approach instead. So I modify this to 6 and 7, and I click on my little info button here, and I see the relevant load combinations given to me directly from the ASCE E7, also with that redundancy factor. I want to do the exact same thing here, but I want to apply this for my unfactored load combination, so 8 through 10. Again, we also have overstrength available in this list as well. So I've now created these two design situations, and I jump to my load combinations, and now I see quite a few more load combinations generated here as well. The problem, though, is that only that static vertical seismic forces are included in these load combinations. I don't see anything to do with my response spectrum analysis. And the problem here is that with load combinations, we are going to take all of the loads at once and then run the calculation. And this is what allows us to take into consideration second order effects like P delta, or even third order effects if we had cables or fabric membranes. Well, if you remember from our response spectrum analysis, we already have the results available to us. So instead, in order to combine these with the other load cases, we have to do this linearly, according to first order analysis, through what we call our result combinations instead. So back under the base tab, I'm going to activate here the result combinations. And what you'll see is that we get a new tab available here, but it's still empty. And the reason why is because under the design situations, we're currently generating still those load combinations. We're going to go in here instead and create a new definition type for the combination wizard settings and toggle this now to result combinations. And it clearly also states linear analysis. We cannot combine second order effects to the results of other load cases or combinations with second order effects. You cannot just sum them up. It will essentially provide incorrect results. So this is why we always have to do this linearly according to first order analysis. So now that this particular setting has been defined, what we can do here for both of these design situations is to toggle to the result combination. And under my last tab here, now I'm finally seeing exactly what I would expect. I see my horizontal forces with this particular load case combined with the vertical, as well as the other load cases. Now, you'll also notice here for that response spectrum analysis within this dropdown, the scaled sums envelope is listed. We could toggle this if we wanted to 100% in the X versus 100% in the Y. But remember, the scaled sum envelopes is going to be the worst case scenario, the envelope solution of all of these options listed here. So we'll likely leave this as is. So now that we have all of the information defined here with result combinations, design situations, we would be ready to move forward with possibly the design of our structure. So for today, maybe we activate the concrete design add-on and move forward with design according to the ASCE. Again, there are previous webinars that will go into a little bit more detail related to this. So sticking with the response spectrum analysis, we want to move into the second part of our example today. And if you remember under this base tab that we have here the redundancy factor that was considered the same in both directions. It could be quite common though that we have a different redundancy factor in the X versus the Y. Same concept for overstrength. It just depends on our structural system if this is applicable to our design. So I do want to move forward with assuming here that we possibly have a redundancy factor of 1.3 in the X direction while keeping a factor of 1.0 in the Y direction. So now this first line is completely irrelevant. We are now focusing on these two separate X and Y directions here. Again, same concept with overstrength. This final line here, this will come into play with the 130% rule. So just keep this in mind. This is currently set at 30%. We'll talk about this in just a minute. So with that said, the problem now, if I go to my load cases tab here, I can no longer consider X and Y together in the single load case. I now need to separate these out into two separate load cases. So the first thing I want to do is to deactivate this previously created load case. It's not enough just to uncheck here to solve. That will just make sure it's not solved for when we go to calculate all. But in order to remove from the actual load combinations themselves or the result combinations, under the Actions tab, I want to go ahead and select the horizontal earthquake forces and uncheck this active here. So now it's completely taken out of the load combinations as well. I will take this load case and I'm going to create a copy here. We'll go ahead and activate this one. And we're going to make some modifications here, beginning with the description. So this is the response spectrum analysis only in the X direction. I'm going to make a copy here, and we want to go ahead and rename this second load case, the response spectrum analysis in the Y direction. Now, going back to this input information under this first tab, really everything stays the same. So no modifications are needed here. But under the response spectrum, we want to ensure that we apply the response spectrum in the X to the load case with X. So we'll go ahead and uncheck the Y direction. And same concept here for our load case in the Y, we want to apply the response spectrum in the Y direction only. So now two separate settings here for each of those load cases. In addition, we now are going to consider this bottom setting, the additional settings X and Y independently. Remember, previously this had no impact, but now because we have X and Y in independent load cases, we want to go ahead and activate this for both of these load cases. And now we get a new tab available here. This is going to apply the X and Y load cases into our result combination, considering that 130% rule. So we activate here direction X with the load case X and direction Y with the load case here in the Y direction. So now we can tell the program, okay, consider 100% of the X with 30% in the Y and vice versa. And you might be thinking, well, wait a minute, back under the spectral analysis settings, I'm already considering the 130 rule. But remember, this is only applicable when we have X and Y in a single load case. This is completely ignored now. Instead, we are referring back to, again, this combination factor here of 0.3, which is essentially going to apply the 130 rule required by the code. And that will make more sense when we get into the result combinations. So now that this information is complete, everything that we've done in the first part of this example is still relevant. The only thing that we can do here is go ahead and visit our result combinations tab to view these in more detail. And sure enough, we have these individual load cases. Notice our drop down here looks a little bit different. We no longer have the 130 rule in the sub-results. We don't have the scaled sum factor. We only have a single result in the X, and we have a single result in the Y. But in this first result combination, I'm applying 100% in the X, 30% in the Y, but remember I modified my redundancy factor in the X direction to 1.3. So that's why I see that relevant 1.3 factor here. I take a look at my second result combination, and I'm applying now 100% in the Y and 30% in the X, but when I consider that redundancy factor of 1.3 times 0.3, I get 0.39. So everything is combined automatically in the program according to the code, according to the various factors. But again, if we have different redundancy or overstring factors, we do need to split those apart into two separate load cases. Okay, so the final topic for today is going to be the scaling of our base shear. And for this, I'm going to jump to the PowerPoint to refer here to section 12914 from the code. And in particular, 12914.1 talks about the scaling of forces. The code tells us that we do need to consider the base shear in two orthogonal horizontal directions, X and Y, and that's certainly what we did today. And from the program, we need to get the base shear from this response spectrum analysis from the combined response. And I will show you in just a minute how we can utilize the building model to get this information about base shear. Well, we compare this value from RFEM to the base shear that's calculated from the equivalent lateral force procedure, section 12.8. So this is done outside of the program. But if we find that this base shear from the equivalent lateral force procedure is going to be greater than the base shear that we're pulling out of RFEM, then we do need to scale our forces by this factor V over V sub T. So this is essentially something that we need to keep in mind with the scaling of the forces. Now, the scaling of the drifts from 12914.2 includes the seismic response coefficient, the effective seismic weight, and if that same base shear that we're getting out of RFEM is less than CS times W, we need to also scale our displacements by this factor CSW over V sub T. Now, again, we might be wondering, okay, how do we take into account these specific factors? Yet again, we will apply this directly in the response spectrum here for that scale factor input. Whether we have the response spectrum in the X and Y in a single load case, or these are separated out into two separate load cases, it is still applied here within the scale factor. So if we have multiple factors, so as I mentioned, we'll talk about the scale factor quite a bit, we can consider all of them at once within this particular input. So it could be additive, so to speak. So going back to RFEM now, I want to quickly show you how you can activate the building model add-on. And for this, I am going to jump to an already saved model here where I went ahead and ran the calculation for these two separate load cases in the X versus the Y that we just talked about. And we can visit our base data dialog box. Under the add-ons, we can activate here the building model add-on. So RFEM is a general FEA program. We are not restricted to modeling buildings in this program. We can really model everything. But the building model add-on is really efficient for defining this more building-specific data in this general FEA program. So back under our Navigator data tab here, when I collapse all of these folders, we now have a new one called the building model add-on. And I go ahead and create a new building story. So now in this general FEA program, we have the ability to define story levels. The program automatically creates our first story level at 11 feet. That's great. I'm going to go ahead and create the additional story levels at the additional locations here. Now, everything highlighted is essentially attached to this story level. The building model add-on also gives us the ability to define diaphragms like flexible, semi-rigid, or rigid. Again, not getting too much into the details today. We do have previous webinars that dive a little bit more into this, but the specific purpose right now is to define these specific story levels. So when this information is input, what I can do here is jump down to the spectral analysis results. So this is my response spectrum in the X direction, my results here in table format. Well, now because we have enabled the building model add-on, we get a new option here called results by stories. And within this first tab, this will actually show us the center of mass at each story level. If we had a rigid diaphragm, we would also see the center of rigidity given here. The second tab is where we can pull out the base shear information. So quite easily, we just refer to this table. The program automatically outputs this base shear here in the X direction. I'm currently looking at my response spectrum load case in the X direction. Alternatively, I could toggle here to the Y direction. And what we would want to compare that to is the base shear here in the Y direction as well. Now, we also are given information about the story shear. So again, just very efficient for getting this information very quickly out of the program for each story level. Could be possible to do this without the building model, but does require quite a bit more work. Now, we also have a couple additional tabs here, including the inner story drift and what we call the sensitivity coefficients. For this, again, required for the building model add-on to be activated. I'll go back to the PowerPoint one more time to talk a little bit more in detail about this, because this all refers to P delta considerations. So for this, we refer to section 12916, which further refers us to section 1287 for P delta. Essentially, we need to calculate what we call the stability coefficient from equation 12.8-18. So we see this equation here, and the building model add-on is actually outputting this directly in those last couple of columns that we saw. So this is really nice, very efficient. We don't have to manually calculate this for the ASCE 7. The code tells us that we can completely neglect P delta effects when this coefficient is less than the value of 0.1. Now we need to further calculate the max stability coefficient according to the equation given here. So when the coefficient that's given to us in the program is in between the range of 0.1 and theta max, we do need to scale our displacements and forces by the factor 1 over 1 minus theta. If we do find that theta is greater than theta max, then the code does tell us we do need to completely redesign the structure as it may be unsafe. So you can see in our example today, we're well below that 0.1 value, so we can neglect P delta effects. But if we were above this, but below theta max, of course, we would want to yet again apply this factor here within the scale factor. So several different applications with this scale factor that may be considered within RFEM. Okay, so we'll go ahead and wrap up our webinar today with a few more slides. I did list here the additional knowledge base resources. So these are technical articles. The PowerPoint is available in the GoToWebinar handout. That essentially goes into more detail for this first one according to P delta consideration. So not only do we have the simple scale factor that we just talked about on the previous slide, if you wanted to consider P delta in more detail with something like the geometric stiffness matrix, this is discussed in this technical article. Also story drift according to the code. So there could be considerations within the ASCE 7 where the story drift needs to be considered at a different location than what the building model is given. So this article will certainly help clarify that. And finally, nonlinearities. So as we know, this response spectrum analysis is a linear analysis. Any nonlinearities are converted to linear elements underneath the hood. So if we have any nonlinearities like tension-only members, this is a great article to refer to and how we can consider those nonlinearities in the modal and response spectrum analysis. Again, these are all hyperlinks provided directly within that PowerPoint handout. So if you liked what you saw today, you have any questions, or you're interested in testing out RFEM with the 90-day trial version, we would love to chat with you a bit more. This is a hyperlink directly to our website, or you can scan the QR code here that takes you to the web form to fill out in order to contact our sales team. Of course, we're always available here with the phone number and email shown at the bottom of the slide if you'd like to contact us directly in our Philadelphia office. Our email is info-us@delubal.com. We will have many more upcoming webinars. We try and do these approximately once per month. You can register at delubal.com under support and learning webinars. As most of you know, I will tend to send out a reminder email about a week before these take place, so keep an eye out for that. PDH certificates will automatically be emailed to all participants who are here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. If you watched with a colleague or you watched in a conference type setting and you yourself did not register with your own name and your own email through GoToWebinar, you will need to request that PDH at the given email address shown here, info-us@delubal.com. So you'll want to ensure that you were here for the full duration. Let us know who you watched it with. And again, we'd be happy to issue you PDH credit if you yourself did not register directly for this webinar. And with that said, I want to thank everyone for attending our presentation today. There will be a short survey that pops up. Would love it if you could fill out some comments about the presentation. And with that said, we hope to see you at the next one. Thank you.